All right, I want to finish up by deriving the equation of geodesic deviation. So I promised you 3 characterizations of curvature. One was the covariant derivative commutation relation acting on tensors of higher rank. That's how we defined it in the end. The other one was the failure of parallel transport around the closed loop. That's a nice, vivid way of thinking about it, calculationally a bit annoying. And the last one was the failure of Euclid's parallel postulate, that initially parallel lines will no longer remain parallel if there is non-zero curvature. And so there's a nice equation, at least of historical interest and also of conceptual interest, not usually of practical interest, called the geodesic deviation equation. So we need some formalism and then a calculation to say what's meant by this. So let's consider a 1-parameter family of geodesics. Right, so a geodesic is just something that satisfies the geodesic equation. We're going to do affine parameterization, sort of always mean that, unless otherwise stated. So, there's a 0 on the right-hand side of the geodesic equation, not some function times the tangent vector. So the picture here is not one curve, but a whole family. Let's draw them kind of like this, but they're maybe spreading out. And for each curve, we would give some x mu of lambda, but we're going to call it t in this case, because we're going to be considering time-like geodesics. I'm not going to say tau because I'm not going to assume the tangent vector is unit normalized, but I am going to assume that it's an affine parameter. So each curve is x mu of t, but then there's a second parameter that describes, which curve you're talking about. So this labels which curve, and this is the affine parameter on a curve. Okay, so a curve is just a function x mu of one variable. A family of curves can be given as a function x mu of 2 variables. Okay, and so just to give you a kind of visual orientation, I'll draw in a cartoon sense that, t goes up and s goes to the right, but this is just a cartoon. So then if you're at some point here, we will have 2 vectors. We will have the tangent vector t mu will be our notation for the tangent vector, and then the other derivative we will call s mu. So this I'm going to draw horizontally here, and that's going to be called s mu. And they're defined just by the way you would expect. So the tangent vector is, of course, just the parameter derivative like we had before, except now I need to write it as a partial derivative. And the deviation vector, s mu, these are definitions, I'll put 3 equals to make that clear, is then the other partial derivative. So the subtleties in applying the geodesic deviation equation are always mapping this deviation vector into what your apparatus measures or something, which you do have to do a bit carefully. But as an abstract statement, it's quite clear that this thing has something to do with how far away a nearby geodesic is, right? We're going to get an equation for the time evolution of this deviation vector, and that's going to be the geodesic deviation equation. This we already have a name for. This is the tangent vector. Okay.
How can we talk about the deviation when we established S was just kind of like a label?
Well, that's S mu. But that's right. There's a lot of arbitrariness here. So if I doubled S, I could double the length of the deviation vector.
Right, but it's not exactly like a position right
but,
now. It's just an arbitrary.
But I can't double S at every point, right? The rule is S is constant on each curve. So the change in the deviation vector is a unique prediction. right? Because if it points infinite, drew it quite accidentally, but now it looks like an advantage to point exactly to this neighboring curve. So if you imagine we work where these two curves are very close and talk about the curve where the deviation vector points exactly to it, then if we change the value of s on this curve, we change the length of the deviation vector, by a factor of 2 or something, but it just changes by a factor of 2 over the whole curve. So its time evolution will have invariant information about how fast that curve is moving away. Yes?
Is this like, it's not literally, but is it kind of analogous to the way we have a gradient of like a field where it's like you point to the next thing?
No, not really. So first of all, gradient should be thought of as a one form. And even when you're in Euclidean space, since you have the isomorphism and you think of it as a vector, it's pointing normal to the level sets of the function. Here, there isn't really a function we're talking about the level sets of. We just have a set of 4 coordinates as a function of 2 parameters. So it's a distinct idea.
Both t and s are finely parameterized?
No, only t. So the rule is s is constant on each curve. So s is constant on curves on the geodesics. And for each curve, t is an affine parameter. No, I don't think it should be thought of as a world sheet. A world sheet would be if we had a physical object that was moving through. It does define a 2-dimensional surface in that sense, but surface is not the right way of thinking about it because we have a preferred foliation of the surface, namely the geodesics we're talking about. No, we're going to derive an equation for it because S mu would be constant in a flat space because of the parallel postulate, but it won't be in a curved space. Yep.
Like you said, s is constant, right? Like, isn't that what finely parameterized means? That
No, it means the tangent vector. The length of t mu is constant along a curve. That's affine parameterization. The length of s mu will not be constant because the geodesics are deviating and s mu is proportional to the deviation. They're going to spread out just like I drew it. Okay, so let's do the derivation. So to start, notice a nice thing about the construction is because we have these partial derivatives, we have equality of mixed partials. So del t mu del s, which according to up here is really the second partial derivative of x mu, mixed partial derivative, that's the same thing as del s mu del t. So by equality of mixed partials, so that'll be a good place to start. And then as usual, we make things covariant. So that we'll end up with a nice covariant equation. So let's do that in 2 steps. So the first thing we can realize is that partial s is the same thing as s mu partial mu. So this left thing I could write as s nu partial nu t mu. And similarly, on the right-hand side, I could write this as t nu partial nu s mu. Okay, so this is just the chain rule. So, partial t is the same thing as t mu partial mu, etc. Now, did I ask you to prove this? This might look familiar. Does anyone recognize if I move one of these to the left-hand side, anyone recognize this equation? Yeah, this is the commutator. If I made this a minus sign, this is the commutator. It's saying the vector fields commute. let's write it out. So the claim is this implies actually that the covariant derivatives del nu t mu equals t nu covariant nu S mu. That's a claim. There's fancy ways to see this involving commutator, but I don't think we've done it. So let's just see the things cancel. That shouldn't be too hard. Move this to the right-hand side. Let's write out the corrections. So this thing with the covariant derivative would be the partial derivative plus some Christoffel. So to go the other way, we need to subtract out the Christoffel symbol thing. So this will be mu nu lambda t lambda s nu on the left-hand side, and on the right, it'll be mu nu lambda s lambda t nu. And if there's justice, these will be the same term. Mu nu lambda t lambda s nu, mu nu lambda s lambda t nu, but the Christoffel connection is symmetric on the lower two indices. So these are the same term. Okay. And so we indeed have S nu covariant nu T mu equals T nu covariant nu S mu. Okay. So now what we've done is we've taken that equality of mixed partials in this construction and made it into a nice statement that just involves tensors and their relationship. All right, now again, this is all a conceptual, an equation to demonstrate a conceptual property, really. So we just make a lot of definitions that seem about right. So we have S is kind of like relative distance, squiggle. It's not physical distance because it's not involving the metric or something, so definitely a squiggle. Well, but it's coordinate separation. It's not really distance, right? So there's no metric involved. It's arbitrary how you parameterize those world lines by S. So it's some notion. It's squiggly proportional to, as if similar to, I don't know, relative distance. And let's define v mu to be yet another derivative. So that'll be another t nu covariant nu S mu, which is the same thing we called capital D S mu dt. And this we're going to think of, as relative velocity, but it's really some arbitrary coordinate-dependent thing. It's just somehow proportional to relative velocity. And then, similarly, we can define capital A mu as t nu coordinate nu S mu, not S mu, it should be V mu. It's a mistake, yeah, it's a mistake in my notes. V mu, which is, of course, now a second derivative, so let's do T nu del nu of, T rho del rho S mu, which you could write as capital D2 S mu dt squared, and we would call this relative acceleration. And that's what we want to get an equation for. Okay.
Why do we specifically want the acceleration equation? I mean, we've been working a lot with velocities, right? Is it that we're trying to get the Newtonian?
Yeah, I mean, velocities are frame dependent, so we expect the physical effects to be visible in acceleration. Yeah, I mean, forces act on accelerations.
Yeah.
So, yeah. Okay. All right, so I think we can do this. As usual, we have our calculation for the last 10, 15 minutes. So now we compute. So this acceleration, by definition, was, I'm just using the indices in my notes. I know better than to try to figure it out live. So I've swapped rho and sigma, apparently, as mu. Okay. I really messed it up. I heard someone say "s," which was enough for me to catch on that there's something wrong. Okay. Now, the next thing we're going to do with this is we're going to use that T and S commute. So it was, you have it written down in your notes, presumably, if you're taking notes. So this T dot grad S can be replaced by S dot grad T. So this step was that commutator of T and S equals 0 that we derived previously. We just noted that the commutator can also be written in terms of the covariant derivative. Then, following my notes, it looks like we're going to use the Leibniz rule. So we'll have T rho del rho S sigma times del sigma T mu plus the remainder T rho S sigma del rho del sigma T mu. So that was just Leibniz rule. Okay, now we'll use the commutator again. So this one will be S rho del rho T sigma. So this is again that T S equals 0 del sigma T mu plus the second term. And now for the second term, we're going to use an equation that hopefully you will soon practice on the homework, but I don't think have yet, which is commuting covariant derivatives. Anyone remember how to commute covariant derivatives acting on a tensor? From last time. It was one of the 3 characterizations of curvature that we gave. Yeah, I know you know this. Yeah, right. So remember, in fact, the definition we chose for Riemann tensor was that when you commute the covariant derivative acting on a tensor, the failure to commute was given by the Riemann tensor contracted with the original one itself. So we can change this to del sigma del rho T mu. According to my notes, I wrote plus. I must have also swapped an index because it should be minus. Oh, no, when you add the commutator, yeah. If I did more quantum mechanics, I would know you add the commutator. S sigma del sigma, very good, of T rho del rho T mu. Okay, so then I need to subtract off whatever I added in by putting the T rho in. So what I subtract off will be S sigma del sigma T rho. And then what's left, S sigma del sigma T rho, is D rho T mu. Very good. And then plus the Riemann stuff, mu nu rho sigma T rho S sigma T nu. Looking good. All right. I heard Evan mumble something about some canceling stuff. Does anyone else see? Yeah, does anyone else see any cancellations besides Evan? Okay, you count. Which terms is it? Okay, first and third are the same. There's a claim because this is S rho del rho T sigma. This is S sigma del sigma T rho, but hopefully this will be rho and this will be sigma. Yeah, so they are the same. And they do have different signs. All right, now somebody besides those three over there who have been talking a lot, see anything interesting about this term here? Does it remind you of any equations or? Sorry? The geodesic equation, that's right. Yeah. Well done. So this is the geodesic equation, T rho del rho T mu, right? T rho del rho is that thing we called capital D by D lambda, or in this case, capital T, right? Capital little t of T mu, right? That is the geodesic equation. This is a geodesic. So by assumption, our affinely parameterized geodesics. This is 0. Okay, so that's our lovely equation that says that this relative acceleration, a mu, is equal to Riemann tensor mu nu rho sigma T rho. How should we write it? Let's write it as, whatever, keep it in that order. Okay, so this is the geodesic deviation equation. So conceptually, it tells you that what is it that determines the local violation of Euclid's parallel postulate? It's exactly this Riemann tensor. Okay, so remember the setup here was our one parameter family of curves with S mu pointing transverse to the curves, T mu pointing parallel to them. And if you want to know how does S mu change as you move along these curves, you have to take the tangent vector and dot that into two of the components of the Riemann tensor, and you have to take the deviation vector and dot that into one of the components of the Riemann tensor. And what you're left with is a one-index object, because the Riemann tensor had 4 indices. So when you dot twice with T and once with S, you get one index left, and that tells you the relative acceleration, so how fast S mu changes with time. So it's just a nice statement that curvature is what makes violations of the parallel postulate. But I would not recommend using this equation in practice. It's very pretty, but it's one of those equations where you've made it look very tensorial by building into your definition of the tensors some arbitrariness. Right? You guys all objected, and rightfully so, that like, what is this S sigma? What is this S? I picked them. Why is that interesting? Okay, so it's a good equation, but not a great equation. It covers up a lot going on under the hood, and I've been burned by it before. I was even burned by it fairly recently reading a part of the book where he invokes this later and gets the right answer, but accidentally. So maybe if we get to gravitational waves, I'll get there. But anyway, that's the geodesic equation. Have a great spring break. Homework will be due the Wednesday following.